Well, today we're going to talk about inverse functions, and that's kind of what this last chapter is. And this is really a good transitional chapter for us because we're going to spend a lot of time talking about functions and actually doing a lot of algebra type work in this chapter along with trig. So we're going to be this is where algebra and trig kind of start merging together a lot more in this chapter, which is good because remember when we come back after for second semester, then we go into the college algebra portion of this class. So we're going back towards algebra again. We're kind of transitioning away from just the triangle solving and that sort of thing. We're still going to be using trig, but we're going to be more algebraic at this point. We're heading kind of towards that direction. And then we get into the second semester, which is all the fun stuff like, complex numbers and logarithms and conic sections and all that advanced college algebra stuff that's going to be getting you just all primed up for calculus next year. Yeah, good times. No? All the people have been going, hey, trig, I love algebra so much more. And start talking with the algebra, you get this look like, I hate algebra. Boy, are you in the wrong place. Okay. Inverse functions. A function h of x is the inverse of a function f of x if for every point x, y in the function f, the point y, x exists in h. A lot of times inverse functions are done with a diagram instead of a verbal definition like that. And basically what we deal with here is you say, okay, this is my domain, and this is my range, and for every element of the domain, the function f of x takes us to an element in the range, right? Fine, we put x into the function, it does its little magic trick, whatever happens with that function, whether it's trig or algebra or whatever it is, logarithms, whatever, and we get out of y. We put it in x, we get out of y. It's the old function machine idea, right? And the inverse function is the function that takes us from the y back to the original x. That's what the inverse function does. So that's the idea of an inverse function. That's how an inverse function works. It's the opposite. It's the backwards. It's the going in reverse. That's how we do inverse functions. So from a diagram standpoint, that's what's going on. For picture people, that probably is a great explanation. For verbal people, this might be better. Please note when we do f inverse of x, f to the negative 1 power of x, because a negative 1 is describing a function that's indicating inverse. Unlike if we put the negative 1 as an exponent on a variable, which represents the reciprocal. That's confusing, but it is a distinct difference. F negative 1 of x, because the negative 1 exponent is on the function and not on the variable, it's representing an inverse instead of a reciprocal. So don't confuse the two. So when we get to, so f to negative 1 of x is not 1 over f of x. It's not the reciprocal of f of x. It's the inverse function of x. Now, with just linear functions or quadratic or algebraic functions, finding the inverse function is pretty simple. And you've done this before. This should be review. To find the inverse function of x, we switch the x and y. We start with, it starts as f of x equals 2x plus 4, where you just change f of x to y, because that's what we're used to doing. Then we switch the x and the y. So we turn any y's into x's and any x's into y's. And we solve for y. So subtract 4 from each side, divide by 2, and there's my inverse function of x. So I'd say f inverse of x is x minus 4 over 2. Okay? So general procedure for finding the inverse function for a polynomial, switch x and y, solve for y. Pretty simple. whatever it takes to solve for y. And you do have a couple of types of those in your homework problems. They tend to be linear. They're not that bad. Not too tough to do. Of course, this is more of a trig class, so we're going to be interested in inverse trig functions, which we've already worked with to an extent. But we'll work with a lot more now. Trig functions do have inverses, but we do have a little bit of a problem. If I just look at the graph y equals sine of x, this is from negative 4 pi to 4 pi, or even a little bit beyond 4 pi. That's a graph of y equals sine of x. Now, this is a function, because if we look at, remember, our vertical line test for functions, if we want to know if something's a function, we create a vertical line, and then if at any point that vertical line crosses more than once, it's not a function, but this passes my function test. For every x, there's only one y, right? So that's a function just fine. The problem is, what happens when we want to go inverse? Well, when I want to go inverse, this is what my function. This is what it would look like. And oh dear, that's not going to pass a vertical line test at all, is it? So the inverse technically is not a function, is it? I don't have an inverse for y equals sine x, an inverse function. I have an inverse, but it's not a function. Because, let's say, for example, even going back here, let's say I do sine of x equals 1/2. Sorry. Equals 1/2. Sine of x equals 1/2. Well, I've got a solution here. I've got a solution here. One here. Got one there. Got one there. Got one there. Okay. You get the idea, right? So if I do the sine inverse of 1/2 and I want to get back to x, which x is it going to be? I mean, which one of these values am I going to choose? So we got basically two different ways we're going to think about this. We're going to think about, well, let's try to choose all of them. And then eventually we'll narrow it down to a primary value that we're going to deal with. Just a primary. We're going to limit the range and the domain of the inverse functions so that we actually get a function. But we can also talk about getting all of them. And today we're going to talk about how do we find all of them. And we've already done this to an extent. All right? This is kind of review. We've done this. And again, we can take a look at this. With x equals 1, for example, we would get a y value here of pi over 2, and another one of 5 pi over 2, and down here, negative 3 pi over 2. And so what we want to do is we want to find a way of expressing all of those using just one little formula. And that's what we're going to learn. That's what we're going to learn how to do. Now, when we write the inverse trig function, there are two different ways of doing it. We can write y equals sine inverse of x, or the more old-fashioned way that the book uses a little bit more than you'll probably see anywhere else, but it's an old book, so we're used to that. Is arcsine. These mean the same thing, sine inverse of x or arcsine of x. So you see one or the other, and they'll use both. Just realize they're representing the same thing. They aren't representing different functions. There would be cosine inverse and arccosine, tangent inverse, arctangent. Same with secant, cosecant, and cotangent. And again, just to note, sine inverse of x does not mean cosecant of x. It is an inverse function, not a reciprocal function. Cosecant is a reciprocal function of sine, not the inverse function of sine. Very important to keep those two things separate in our mind, reciprocal versus inverse. So, if I ask to find the solution to sine inverse of 1/2, we first look for the primary angle that gives us that. What is the first angle that we come across in our 0 to 2 pi progression that we normally deal with, what's the first angle we come across that has a sine of 1/2? Well, it starts at 0, then the first angle is 1/2. Oh, that'd be 30 degrees, wouldn't it? Okay? So the first angle we come across is 30 degrees. Whoops, there we go. But we want to pick up all the angles. Now, because sine, we can go back to our circle definition here. Go back to our unit circle from chapter 1. I'll even draw a nice circle by letting the computer do it for me. Look at that. Nice unit circle. Okay? We know that 30 degrees is coterminal with 30 plus 360, right? That's also 390 degrees. Would also have a sine of 1/2, wouldn't it? And if we went around another time, I'd be at 750 degrees. If I went around another time, it'd be at 1110 degrees. What are we doing each time we go around one unit circle? How many degrees are we adding each time? 360. So the way we're going to express this for now is we're going to say, okay, we got our primary answer, 30 degrees. Oops. 30 degrees plus 360n, where n is an integer, which means that it could be a positive rotation or a negative rotation. Instead of adding 360, we could subtract 360. Negative 330 degrees is the same as positive 30 in that circle definition, right? So that's our solution. That's one of our solutions, or one set of our solutions for sine inverse of 1/2. It's 30 degrees plus 360n, where n is an integer. But there's another solution too if I look at this, because again, sine is measuring the x. What's the other angle that has a sine of 1/2? What is the other angle in the 0 to 180 range? 150. So that's a secondary solution as well. So not only do we have 30 plus 360n, whoops, I'm going here this way too, we also have 150 degrees plus 360n degrees. So we don't get a single solution, we get sets of solutions for sine inverse of 1/2. There's an infinite number of answers. And what I've done here, instead of using the unit circle definition, is here we've drawn out the sine graph solution. We see the same thing. We see the same thing, that sine is 1/2 here at 30 degrees, and again at 150. So a different way of looking at that same idea. Where are my two solutions coming from? And then when does it repeat? Because a periodic function, what's the period of the function? 2 pi. It repeats every 2 pi units. Do you remember kind of doing this before? We've kind of done this before. Is it making a little more sense maybe the second time around when you're thinking about this now? Now that you understand your charts a little bit better and the way that the sine and cosine are working? So if I would say sine inverse of 1/2, my solutions would be 30 plus 360n and 150 plus 260n. Now, the primary solution is going to be the 30 degrees. That's what we're going to consider our primary solution for that, between negative 90 and 90. That's where we're going to find our primary solution. For cosine, so for sine, our primary angle is always between, and I'm not sure if, do I have that written down? For sine, the primary angle, here we go. I did kind of gloss over that. I should highlight that. For sine, the primary angle is always between negative 90 and 90 degrees. Why? Because, and we can see it in either the circle definition or the other one, sine associated with the y between positive 90 and negative 90 gives us this whole arc. Or in other words, all possible values, can't we? For sine, happen between negative 90 and 90. Between 0 and 180, we actually duplicate values with sign. I can see that again on this graph. If I went back to negative 90 back here, okay, between negative 90 and 90, we get the whole range of values between negative 1 to 1. From 0 to 180, we repeat values. We don't want to get repeated values. So for sine, my primary angle is always between negative 90 and 90. And if you put it in your calculator with sine inverse, you'll always get a solution between negative 90 and 90. For cosine inverse, we go between 0 and 180. And again, we could see that. Do I have a cosine graph here? No. We can see that from a sketch of the cosine graph, because if I look at my cosine graph, there's 180, there's 90, okay? Between 0 and 180, again, we get the full range of the function from positive 1 to negative 1. So my solutions for cosine inverse are the primary angle plus 360n, and then the second angle, whatever that second angle is on that 180 to 360 range, wherever that second solution is going to be, plus 360n. And we just keep adding 360n, 360n, 360n. The only exception to the adding 360n to these is when we're dealing with solution of 0. Whenever we're dealing with sine inverse of 0 or cosine inverse of 0, we do plus 180n, because the zeros happen every 180 degrees. It's just the nature of the function. You don't need to come up with a secondary solution for 0. You only need the primary. So you go 90 plus 180n for 0, because every 180 degrees it's going to be at 0 again. So that's essentially what's going on today. It's not that earth-shattering. It does help to know, obviously, your values of the functions. We are back to where we can use a calculator again, if necessary, but the calculator is not going to help you find the secondary angle. It'll only give you the primary one. You're going to have to know your graphs and stuff to find the secondary angle. So types of problems we're going to see today. Yeah, 3 through 14 are all just polynomial functions, switch x and y and solve for y. And for the most part, 15 through, they're very much identity angles. So it'll be things like find the cosine inverse of root 3 over 2. And say, okay, where is the first place where cosine equals root 3 over 2? Well, that would be what angle? And we can work in degrees here. 30 degrees. Okay, cosine of 30 is root 3 over 2. So it'd be 30 degrees plus 360n. Where's the second place that cosine is root 3 over 2? And again, here's where knowing my graph really can be helpful. Gosh, it was 30 degrees in here, right? So that means symmetry, it's got to be 30 degrees in here, and this is 360. So that's 330, right? So my second angle would be 330. Or if you prefer, you could also say negative or for the second one, negative 30 plus 360n. In fact, it might be easier to just do 30 and negative 30, because that's the symmetry for cosine. So finding that secondary angle is going to be the biggest trick for some of those. The primary should be pretty simple. The other types of problems, like I said, you'll see as they say, find the inverse function, y equals 1/7 x minus 9. Find the inverse function. Well, gosh. X equals 1/7 y minus 9, and now solve for y. X plus 9 is 1/7 y. I guess I can multiply both sides by 7. Y equals 7x plus 63. There's my inverse function. Pretty easy. Good exercise in algebra, though. So let's bring up the assignment. That pretty much covers what we're doing. We're going to talk a lot more about the trig functions and stuff tomorrow. Not sure if I updated the assignment sheet or not, but I know I've got it on my... I think I need a new assignment sheet. Yeah, I did not yet do that. So we'll go here into my iWeb. Okay. That's fine. Here we go. This is my archive. I've got my live one, and this is in my archive. So there you go. Page 253, 11 through 26. These are all pretty short, quick little problems. 27, 29, and 31. Yeah. You do not, for today, for 27, 29, 31, you do not need to graph. Okay, you can skip the graphing portion of it, just find the inverse function. All right, so graphing is not necessary. By the way, 19 through 26 want us to do the inverse functions in radians, which is fine. Just give the radians, instead of adding plus 360 n, what are we going to add? 2 pi n, right? Give the primary in radians, secondary in radians, and add 2 pi n instead of 360 n. So 11 through 26, 27, or I should say 11 through 27, 29 and 31. That'd be the easier way of doing it, wouldn't it? Okay. Thus endeth the podcast.